Is it recording? Alamak, saya mute korang. Did anyone ask me any questions? I muted you guys. Tak ada kan? Alright. So we are doing chapter 8. Where is my first slide? Oh, it's this one. Okay, so chapter 8 is on rotation of rigid bodies. So in chapter 7, we talked about rigid bodies, right? We did talk about rigid bodies. And rigid bodies is an object that when it moves or when it has motion, it does not change shape. So if the object is moving from point A to point B, we are expecting it to not change in shape. That is a rigid body. So rigid body is actually everything in like us. We are not going to change shape as we walk. The car is not going to change shape as it moves. So those are rigid bodies. So for chapter 8, we are discussing about the rotation of these objects, right? Previously, we talked about the linear motion, the motion in the X, the motion in the Y, and if it's flying or not, if it's, and then we talked about circular motion of objects, but now we're talking about rotation of rigid bodies. It's slightly different than centripetal acceleration, and we will find out how. So for this chapter, oh kenapa dia 7.1? Ini tersilap. So chapter 8 talks about torque over force, equilibrium of a rigid body, dynamics, if it's moving, how do we find out the forces acting on it? And then we talked about rolling motion, and we connect the objects with rotational and linear. So remember I told you guys yesterday, this is translational. You have movement in the X and Y. This is the linear part, and then we have the rotational movement. So when you combine this, it is called a rolling motion. It's called a rolling motion. How is that? How does that look like? So you have a ball, it's rotating, it's also moving forward. That is both translational and rotational. So that is a rolling motion. So rolling motion ni is something new. Kita akan belajar nanti. It's very interesting. And then this is like the introduction part, and this part kita akan belajar further lah, deeper into the rolling motion. Okay, so let's continue. So for this chapter, we will try to define and calculate the torque of a force, solve problems on equilibrium of a rigid body. We've heard about equilibrium before. It was equilibrium of force, right? So equilibrium means that the object is not going to move. But what does it mean when you have an equilibrium of rigid body? What does it mean by that? It's not rotating. So nanti kita akan belajar. Solve problems on kinematics of rotational motion. We have talked about this in previous chapter. Hello, kenapa saya tak tulis ni? Okay, boleh. Solve problems on kinematics of rotational motion and solve problems when the object is rotating. Okay, this one is in equilibrium, it's not rotating, but we know that it is supposed to rotate. This guy, it is rotating. Okay, so those are the two conditions that we will talk about. Okay, so what causes rotational motion? So I really like this chapter, but most students find it a little bit hard. And I'm going to try my best to not make this feel that way because it's supposed to be fun. This is about torque. Okay, so to make an object start rotating, it not only depends on the force, but also on the position and direction of force. So this is our first statement here. What do we have here in our figure? This is a door. Okay, we're talking about the door here. So if this is Hazira, Hazira is walking and she sees a door. She sees a door, this is the doorknob, and this is the hinge. Do you guys know what a hinge is? Engsel, eh? Kalau tak tahu, pergi tengok pintu sekarang. So this is the door, and the door has hinges. Okay, so we know that when we open the door or when we close the door, the movement is at the hinge. It is rotating at the hinge. It is either going to open or going to close, but that movement is at the hinge. Without the hinge, it's not going to be able to move forward or backwards, right? Without the hinge, it's not going to move like that. So the hinge is our axis of rotation. Without the hinge, there is no rotation. So this is your axis of rotation, ataupun the axis of rotation of Hazira's door. Hazira jadi mangsa hari ni, sorry Hazira. So you have your door, you look at it. When you open the door, it moves at the axis of rotation. You can either move it towards yourself or away from yourself. And without the hinge, what happens? You can only like cabut pintu tu or letak balik pintu tu without the hinge. You have to like move it, right? Move it somewhere else so that you can go through the door. But we don't want that. So the hinge helps us to rotate the door. That is a rotational motion. Whether you like it or not, it is rotating. So Hazira tries to push the door. She wants to close the door, right? So she applies a force over here. Okay, you can try it yourself. So she pushes the door at this point, point number 1. Let's call this point number 1. She pushes it that way. And then dia cakap, oh, susah lah nak tolak kat sini. And then she tries to push the door over here, point number 2. Okay, she pushes it. Can you tell me at which point is it easier for Hazira to push the door? Is it
2.
point 1 or point 2? Point 2. And this is why our doorknob is over there, right, at the end, because it depends on the position of the force. So they want you, hey, can you please apply force at the end of this pintu? But this is not like common sense to everyone. So they put the doorknob there so that, you know, everyone has to use that doorknob and at that position, right? So if Hazira pushes at point number 2, it becomes easier rather than if she pushes at point number 1. And why is that? This is actually related to torque. This is a new term, torque. We call this symbol tau. It's a Greek symbol. It denotes torque. Okay, so torque is given, the equation for torque is R cross F. R cross F. So what is R? R is the distance of the force from the axis of rotation. Okay, so that's not really clear. Let me use a different color. Blue. Let's use blue. Will that help? Yes. So this is going to be R. R is the distance at which you apply force with respect to the axis of rotation. So the greater your R, the easier it is, or the greater the torque that you have. And the greater force that Hazira applies, the greater the torque that she has. I mean, the door has, right? So if you increase force, you are increasing torque. If you are increasing the radius of the force to the axis of rotation, you are also increasing torque. So a greater torque gives you like better, senang sikit lah nak tolak, senang sikit, and this is what we want lah. The aim is to have high torque. Okay, so now this is like a door, right? So let's go over here. Ni gambar daripada atas. This is like, imagine this is your eyes, you're looking at it this way, and this is what you see from the top. This is your top view of the door. Okay, so this is your hinge over here. This is your axis of rotation. Okay, and Hazira applies the force at point B and the force at point A, but we called this as number 2 and number 1, right, previously. So for the force at point A, it has a greater R. For the force at point B, it has a smaller R. Okay, so to make an object start rotating, it not only depends on the force, but also the position and direction of the force. So this is what they mean, what causes the rotational motion. Okay, so I told you about torque equals to R cross F. R cross F, when we expand the cross sign, we know that it is supposed to give us a sign. Previously, we talked about work done, right? Work done was displacement times force, right? F dot D or F dot X. How did I expand this? How did we expand this equation? Do you guys remember?
F cos D.
F
cos theta D.
times theta D. What does the theta mean? What does it refer to? Ingat lagi tak? What does it refer to? What does this angle refer to? So if I have force this way, and I have, but the displacement, okay. If my displacement is this way, but I apply my force this way, what does the angle represent?
Angle between force and displacement.
Yes, angle between the force and the displacement. So if I extend this, I can say, okay, this is the angle. And what does the dot product mean? Ingat lagi tak apa maksud dia? What contributes to work done? The parallel force or the perpendicular force?
Parallel.
Parallel, right? So only the parallel component of this force contributes to work done. This is dot product. Only the parallel force contributes to the work done. This is chapter 4, I think. Okay, so dot product, when we expand it, it gives us F cosine theta D. Cosine theta is the angle between the force and also the displacement. For cosine, we want to find out what is the parallel component of the force to the displacement. Okay, kalau kita ada resultant force pun, when we have angle, this is F and this is my theta. I say that the axis that touches the angle gets the cosine and the axis that does not touch the angle gets the sine, right? And when we have cosine, we want to know what is parallel in this direction. Okay, so that is your dot product. Now let's go back to torque. Now torque tells us tau equals to R cross F. Cross means that only the perpendicular component of the force has a contribution to torque. Only the perpendicular component. This is what the cross product means. Component contributes to torque. So if I have a parallel component to R, I don't really care about it. It doesn't give me any torque. But if I wanted to talk about work done, then I care about it. I want something that is parallel to my displacement because this is a dot product. When we're talking about cross product, we only care about the perpendicular component contributes to torque. Okay, so now let's take a look at the Hazira example. So here, if Hazira applies a force over here, this is my force, and this is my axis of rotation. This is my R. This R is the axis of rotation to the point where we are applying force, right? Does this contribute to rotational motion? Can we push a door dekat hujung macam tu?
No.
Will it move?
No.
Have you guys tried it? Confirm ke tak gerak? Kita nak cuba ke? Tapi saya kena bawa saya punya laptop ke rata-rata and you guys will see my room that it is a mess. So I'm not going to do that. Okay, so you can try it yourself. So tolak pintu kat hujung tu and you can see if it is going to move or not. But my best bet is it's not going to move because torque wants something that is perpendicular. So kalau Hazira tolak kat sini, dia membuat kerja sia-sia. Macam itulah cerita dia. So Hazira kena apply force that is perpendicular to the R. Hazira has to apply force that is perpendicular to the vector R. R is a vector. Now again, torque is R cross F. This is when we expand it, it becomes R sine theta F. Theta is the angle between R and F. These are two vectors. So in this case, we have 90 degrees. This is F, this is R. The angle between them is 90 degrees. R sine 90 F. This is 1. So if you apply a perpendicular force, you get the maximum outcome. If you apply at some angle, let's say you apply this way, you have to resolve this F to become perpendicular. So it becomes F perpendicular lah, okay? F perpendicular. And then, so you won't get like the maximum lah. So if you apply 10 Newton, you will get like the component of 10 Newton. Let's say you get 8 Newton for your torque. So berkurang lah. So the best is to always apply a perpendicular force that is 90 degrees. Sama juga tadi Hazira apply parallel. So parallel means that our angle is 0. The angle between F and R, they are the same axis. So the angle between them is 0 or 180, right? F is this way, R is this way. Angle between them is 180. So sine of 180 is 0. Is it? Yes, it is 0. So there's no torque. There's no rotational motion. Okay, so that's your introduction. Let's talk more on it. Okay, I need to tell you guys the definition. Okay, so this is torque. For this equation, RF sine theta, it gives us the magnitude. It does not give us a direction. This is the magnitude. So T is torque, R is the radius or lever arm, the length of the lever arm. You can call it radius or you can call it lever arm. I like to call it radius because it's easier. And then F is just your regular force and theta is your angle between F and the lever arm or your radius. So here, when you're talking about torque, the first thing that you should do is to define your axis of rotation. Always define your axis of rotation as your priority because from there only you can define your R. Without your axis of rotation, you won't know what your R is and you can't calculate torque lah. Okay. So here they are applying F this way. This R is over here. So the angle between them is theta. Macam ni. Dia apply macam ni Anggaplah ni pintu This is pintu. F is applied this way. So the angle between them is theta. So the tangential component, I'm just going to say the perpendicular component here. So the perpendicular component is this way and this is the parallel component. Basically, we have to use our chapter 3 knowledge to solve this. Okay. Okay, so this is an example of torque. Yang ni saya tak tahu nama dia apa sebenarnya. Saya lupa nak Google. Apa nama dia? Wrench. Bukan. Is it a wrench? Bukan kot. Entahlah.
Pipe wrench.
Apa nama dia?
Pipe wrench.
Pipe wrench. Okay, okay. Thank you. Wah, ada orang pernah pakai kot. Okay, pipe wrench. This is called pipe wrench according to your classmate. Okay, I believe him. So here, if you put your hands over here, gemuknya dia punya sound. So, if you put your hands over there, it's going to be hard lah kan untuk macam nak rotate. So the longer your pipe wrench, the easier it is for you to do that rotational motion. You can try it yourself. And then the same case over here, if you're trying to change your car tires, I haven't done that before. So the longer this thing is, the easier it is, the less force that you need to apply. So if you put your hands over here, it's going to be hard. So now you know, so don't do it. So the perpendicular distance from the axis of rotation to the line along which the force acts is called the lever arm or radius. You can just call it lever arm or radius. So in this case, let's label the R and the axis of rotation. So the axis of rotation for this guy over here, lemak tak kena pula dah. Okay, it's over here, right? This is the axis of rotation. And your R is from the axis of rotation to the point that you are applying force. So this is your R. Yes, okay. So that is your R. This is the axis of rotation. And your force, I don't know whether it's this way. Tak tahulah kan orang tu dia nak gerak arah mana. So this is where it is. And then for this guy, your axis of rotation is actually over here. This is the axis of rotation. What does axis of rotation mean in BM? It's called paksi putaran kan? Okay, paksi putaran. So this is where everything berpaksi. I don't know. Axis of rotation lah. Okay, I hope you guys get it lah. So this is where your rotation berpaksi lah. Okay, so this is your R, and this is whatever F that you're applying, whether this way or this way, I don't know, depends on that person. So let's just label it over here. So F, this is your R. This is your axis of rotation. So what did I do here? The first thing that I did was I needed to label my axis of rotation. Without it, I wouldn't know how to label my R and also my F. So yang the examples that we talked about here in general, kita tak cakap pasal equation pun lagi. The examples that we talked about here are examples of single force. Only one force is acting and only that contributes to the rotational motion. Don't know why I'm stuttering today. So in this case, we have like a circular rotating door. I don't know if you guys have seen one, tapi selalu at lobbies lah, lobbies of like high-rise buildings, they have it. It is a circular rotating door and you can go like 4 people can go inside here. And if for this example, we have like 2 people, right? And these 2 people, they are applying force this way. This woman is applying force this way. This guy has R that is shorter. This lady has a R that is longer. So what happens to the system of this rotating door? So we have to add them together because they are vectors. So here we have our torque number 1. Sorry, this is number 2. This is torque number 1. This is torque number 2. So if we have 2 torques, we add them just like we add forces. We add them as vectors. Okay, so that's another issue. First, we need to know how to find torque. Second, how do we add them together? So we'll talk about that. So here, the torque for this guy, okay, since the angle between them is 90 degrees between F and R, so I'm going to write it like this, R2 sine 90 F2. So this becomes 1, so it just becomes R2 F2. So this is the magnitude for torque 2. And then for torque number 1, this is the magnitude equation. R1 sine 90, the angle is also 90 degrees, F1. So this becomes 1, and the magnitude is just R1, F1. So you add them together as magnitude. Nanti kita cakap pasal adding torques together later. Okay, so motion of a rigid body can be translational, linear, right? We can either move X, we can either move Y, we can move Z. So this is translational, the change in position, linear. And then we have rotational, we talked about that. The movement of a globe, your classmate mentioned that yesterday. And then the combination, the movement of a ball. It's moving forward and it is also rotating. So that is a combination of translational and rotational. So a rigid body in equilibrium must not perform both translational and rotational. So now we have net in the F is equal to 0, and another one is net in the torque is equal to 0. This is for translational and this is for rotational. Okay, for translational, kita dah khatam. Kita dah cakap in many chapters already. Chapter 3, chapter 4, chapter 6. Semua dah cakap pasal ni, translational. Net in the F is equal to 0. Therefore, your system is in equilibrium. However, if that object has the tendency to rotate, and not objects has this, for example, I have like my calculator, it does not have the tendency to rotate. So I can just say net in the F is equal to 0. I immediately know that it is in equilibrium. But for something that can rotate, for example, this guy, if I put it down, I know that it can rotate. So it has that tendency to rotate. So I have to like have two conditions. If this guy is supposed to be in equilibrium, it is not supposed to be moving. It's not supposed to be moving in position, and it is also not supposed to be rotating. So there's two conditions here for something that has the tendency to rotate. So just an additional condition, we will talk about this. A rigid body in equilibrium must not perform translational and rotational. So this is something new condition for you guys for equilibrium. So for transitional motion, just a refresher for you guys. If we are saying it has no acceleration, then A equals to 0. For equilibrium, A is equals to 0, right? It means that V can be 0 or V is constant. These two mean A equals to 0. When acceleration is 0 or when a system is in equilibrium, it can either mean the velocity is constant or the velocity is 0. It is at rest. So this is when the system is in equilibrium. For translational motion, so this is for net in the F. V constant ataupun V at rest. Dua-dua ni membawa maksud A equals to 0. When you have A equals to 0, ini membawa maksud net in the F equals to 0. So this is translational. Kita dah belajar ni. Next, when we're talking about rotational and something that is in equilibrium, an object that has the tendency to rotate and it is in equilibrium, it means that it has no angular acceleration. And this can mean no rotational motion at all, or it has uniform motion. So when we have omega that is constant or omega that is at rest, this means our alpha angular acceleration is equal to 0. This also means our net in the torque is equal to 0. Okay. So dia macam kita convert notations last time, yesterday. So omega is V, right? V can be constant, V is at rest. This is A. V that is constant and V that is at rest is equal to A equals to 0. This is net in the F equals to 0. This is translational. The one in pink is translational. The one in green is for rotational. Okay. Kenapa saya bergerak? Okay, so any questions so far? Ush, lama ni saya lecture. Tak rasa pun. Any questions? Everyone is okay? Everyone still following me? Everyone still awake? Okay, eh?
Okay.
Sekejap, Okay, so forces on a rigid body. Kita akan cakap pasal free body diagram again. Because we have that net in the F equals to 0, net in the torque equals to 0. So obviously we will talk about free body diagram again. So sama juga, the forces acting on a rigid body or something that has the tendency to rotate is also the same thing as for translational motion. The forces, there's no new forces. That's great news, by the way. So we still have the gravitational force, the reaction force, the frictional force, the tension force. So semua ni kita akan pakai balik for this chapter. Okay, so problem solving strategy, choose a convenient 2D rectangular axis, resolve all forces into the chosen axis. Can be X, can be Y. Now you're asking me, tapi kan ni kan rotational, kenapa ada X and Y? Apa, nanti kita akan discover. Apply the first condition of equilibrium. Remember, this is for translational. You cannot have net in the Fy equals to, you need to have net in the Fy equals to 0, net in the Fx equals to 0 for your object to be in equilibrium for translational. And then for your second condition, it's not supposed to rotate, net in the torque is equal to 0. So you have one condition and the second one is this guy. Okay. Okay, so we come to our first free body diagram untuk rotational. Okay, I want everyone to focus. This is our first example. Please ask question if you do not get it. Okay, so here we have a seesaw. And we have one adult over here. I'm going to call this adult. Oh, I have someone in the chat. Oh, sorry. Akila jawab soalan. Saya nak panggil siapa hari ni? Anik lah. Anik and Taiba. Oh, saya dah lama tak panggil Taiba by the way. So this is Anik and Taiba. They are not related in any way. It's just an example. Okay, so Anik is here. Taiba is here. This is Taiba's weight, W1, weight number 1. This is Anik's weight, weight number 2. This is the weight of the beam. Now, why is the weight of the beam here? Can anyone tell me? Sorry, weight of the plank, the panggil plank. How did we define our weight for free body diagram?
mg.
mg, betul. Tapi saya tanya, why is this position chosen? Okay, we have a chat over here. Let me read it.
Center.
It has to be center. Siapa yang jawab tu?
Saya.
Saya tu siapa? Saya tak tahu, tak nampak.
Iqbal.
Okay, Iqbal. Thank you, Iqbal. Betul. It should be at the center mass. Remember? Rachel dah buat video pasal ni. So, center mass, right? Zafran is asking, it is in contact with the surface. What do you mean, Zafran? Boleh explain tak? Zafran? Ke saya panggil Aliman? Zafran kan?
Never mind, Doctor. Saya confused dengan R.
Sudah faham ke? Apa yang
Faham,
awak
Doctor.
faham? Apa yang awak faham, Zafran? Cerita sikit. Nak tahu juga.
Saya faham mass dia dekat tengah tu sebab dia center of gravity.
Oh, okay. Okay, betul-betul. So, saya ingatkan awak tanya pasal R. Okay, good one, Zafran. Alright, so we defined our mg's. Weight 1 equals to mg, m1 g, m3 g, m2 g. Ni recap balik chapter 3. And then we have R. Why do we have R over here? What is the condition to have R? What is R? R is reaction force, right? What is the condition to have R?
In contact with the surface.
It has to be in contact with the surface. Okay, betul. So this plank is in contact with this benda Allah ni. I don't know what it's called, but it is in contact. So we say, okay, this is the R over here. So for the torque, net in the torque, so weird to say that. Net in the, do I have another way to pronounce this? Net in the torque, net in the T, no, I can't say T. So net in the torque is equal to, okay, first of all, net torque is equal to RF, right? So we have our first torque over here. Sorry, our first torque is Taiba, our second torque is Anik. They both can contribute to the rotational motion of the seesaw. Okay, they both can contribute to the rotational motion of the seesaw. This seesaw has the tendency to rotate. So this is why we are trying to find the torque. So torque for Anik, let's call this torque number 2, R2F2. In this case, F is W2, the weight of Anik. W is a force. So I'm going to write this again, R2 weight 2. Ataupun M2G lah. I think we are more comfortable with M2G. Because W is confusing, it can mean work. So R2 M2G, this is the weight of Anik and this is torque 2. Do I have to include the angle between R2 and M2G over here? What is the angle between them? Between R and M2G?
Yeah,
Apa? 90. So 90, sine of 90 is just 1, right? So this is why there's no sine of 90 here. But you can write it if you want. So it becomes sine 90 M2G. Boleh. Dua-dua boleh. Dua-dua betul. Tak letak sine 90 pun boleh. Asalkan fahamlah kenapa dia tak payah letak. Sorry. Okay, so this is Anik's torque. Now let's talk about Taibas torque. Excuse me. Taibas torque is torque number 1. Sorry. R1. And then Taibas weight M1G. Kenapa? RF kan? The F that is exerted by Taiba is her own weight. So R1, M1G. Kat sini Taiba and the radius is 90 degrees. So we are just ignoring the sign 90. Excuse me. So now we have two torques. One is this way and the other one is this way. So now let's imagine this is the seesaw. Nampak kan? So this is my axis of rotation. This is the seesaw. So if Taiba is applying weight over here. Korang nampak ke saya? Okay, korang please look at my, what do you call this? Video. Can you guys see me? Please put it into speaker view. Okay? Okay, I'm going to explain the axis of rotation. So imagine this is your seesaw. Walaupun dia calculator. So imagine this is your seesaw. Taiba is sitting here. Anik is sitting here. Taiba applies weight over here. Which direction is Taiba moving this seesaw? Is it clockwise or anti-clockwise? Okay, Taiba apply sini. Okay, imagine kat gambar kat sini. Is it clockwise or anti-clockwise? Anggap Anik tu tak ada.
Clockwise.
Clockwise.
Clockwise? Are you sure? Gambar ni, tengok gambar ni. Gambar dekat dalam slide.
Anti-clockwise.
Anti-clockwise. Anti-clockwise maksudnya berlawan dengan jam. So kalau Anik tak ada kat sini, Taibah aja ada kat situ. Taibah letak aja, tak ada letak. Dia duduk je atas seesaw tu, benda ni akan gerak ke bawah. And that is anti-clockwise. Okay, now can we guess what Anik direction punya torque is? Is it clockwise or anti-clockwise? Again, Anik is here.
Clockwise.
So Anik will go clockwise. Okay, so now they are rotating. They are rotating the seesaw, but they are rotating in different directions. Now, untuk torque, especially for torque, anti-clockwise will be positive and clockwise will be negative. Just like forces, we had the positive and the negative. To the right was positive, to the left was negative, going upward was positive, going downward was negative. Anti-clockwise for rotational motion is positive and clockwise is negative. Okay, now kita boleh kecilkan balik muka saya ni. So here W1 ataupun M1G, this is L, this is the radius. The radius is L. So this guy is positive. And Anik applies a negative torque to the system. So it's minus W2X. What is X? X is the R. The R is the force distance to the axis of rotation. This is the R for Anik. And this is the R for Taiba. R Taiba adalah L. R Anik adalah X. Okay, so this is how you add them together. You need to know whether they are applying clockwise or anti-clockwise. If they are both applying clockwise, then dua-dua akan jadi negatif. If they are both applying anti-clockwise, dua-dua akan jadi positif. Tapi kalau Taiba apply clockwise, Taiba akan melayang. So tak boleh. So please use common sense, use your logic to determine. You can just imagine it like this. Boleh use a ruler, try to use your logic, try to imagine whether it's going anti-clockwise or clockwise. Jangan buat benda yang tak logik nanti kesian Taiba. Okay, so does anyone have any questions about this equation, specifically this equation? So everyone's okay? All right. So next we move, okay, thank you. So we move to the force. This is rotational and this is our translational. So we have to define for both. So for force, kalau kita nak solve for force, translational, we have to combine, we have to group everything to the center of the mass. We assume this is a one whole system. Semua berlaku kat tengah-tengah. So we have R going up we have weight of Taiba, we have weight of Anik, we have the weight of the plank. So this is if we are talking about forces. So everything has to be centered at the center. Okay, this is how we deal with forces. This is what we did for chapter 3 anyways. Dia rata-rata pun friction sebelah sini. Orang tolak sebelah sana. Tapi kita semua kita kumpulkan kat tengah kan for free body diagram in chapter 3. So this is the same thing. We have to combine, we have to like group everything at the center. This is specifically for force. But for torque, we have to define whether it's going anti-clockwise or clockwise. Okay. So for this one, net in the Fy is R positive minus W1 minus W2 minus W3. So if they say that this seesaw system is not moving, this is going to be equal to 0. And if this is not moving, this is going to be equal to 0. Tapi dia tak cakap pun. Kat sini kita nak tahu free body diagram sahaja. Okay, moving on. Next one. This is a suspended bar. So ni dinding, this is your wall over here. This is a hinge over here. This is a beam. Okay, so boleh bayangkan. So when we have a hinge, we know that it can go up and down. There is some rotational motion. It can go here, it can go here. Then we have a string over here, a cable that is connecting the beam to the wall. So here there is no hinge, which means that this is fixed. It is fixed. So there's no rotational motion. Where is my axis of rotation? Where is it? Is it here?
Oh.
Is it here? Or is it here?
Second.
The second one. What is second? Okay, 1, 2, 3. So does everyone agree that the rotational motion is at number 2? Confirm.
Yes.
Confirm eh?
Yes.
Okay, betul. Yay. So kita rotate kat sini je lah. Kalau rotate kat atas ni macam mana kan? But it's fixed. So when we have rotation over here, so we can define our R. Okay. So for torque, sorry, before that. So we have L as our radius for T, tension. When we have a string, we will always have tension. Tension is always pointing towards the center of the string. And if we wanted to know what is the tension over here, it is this direction. But we don't really care about this tension over here. We want to know the tension over here. So this is what we're going to deal with. So tak payah letak kat sini pun tak apa. But direction wise, you need to know which direction tension is. So tension always points towards the center of the string. We have some angle over here. This is the weight of the beam. Okay. And here is our axis of rotation. Now, previously, when we talked about the seesaw, we defined the R. We defined the R as a straight line. So the axis of rotation, this selalu akan ada R because it has that some point of contact that we are interested to know. We don't know the direction of our R sebab dia bergerak-gerak kan? Dia bergerak-gerak, so we don't really know what is our R. So we just define our R as Rx and Ry. This is reaction force that is unknown. So the reaction force can either be this way, this way, this way, tak tahu. We are trying to find it. And it is at the axis of rotation. Sepatutnya saya define for the seesaw the same case. But kat sini dia macam stable kan. Dia macam tak bergerak. Benda ni tak bergerak. It's just a straight. We're like assuming that Taiba and Anik ni macam tak bergerak. So R dia static je lah kan. But here, this thing kita assume dia bergerak lah. Okay. So we don't know which direction our R is. So kita akan define macam ni. Rx and Ry. It is at the axis of rotation sahaja. Okay. So now let's recap what we have here. we have Ry, Rx at the axis of rotation. We have T, tension of the string. We have the weight of the beam. And this is L. So, let's talk about the torque of each forces. Kita akan cakap this as number 1, this as number 2, and this as number 3. Okay, so torque number 1, it should be Rf, right? So torque number 1 is Rf. What is my R? What is my small r? What is my radius for this one? For the reaction force, what is my radius? What is the definition of radius? It is the distance between the axis of rotation to the force. So what is the distance? It is on top of the axis of rotation. That's your hint. What's the distance?
0.
0. There's no distance. It is exactly at the axis of rotation. So the torque for the reaction force is equal to 0 because it is at the axis of rotation. So again, let me go back to the seesaw example. I didn't calculate for the torque of this guy. I didn't calculate for the torque of this guy. Why is that? Because it is at the axis of rotation. It does not contribute to the rotational motion. Kalau kita duduk atas ni, we sit here, there's not going to be a rotational motion because it is at the axis of rotation. There's no radius, therefore there's no torque. Okay, boleh imagine macam tu. When you are sitting at the axis of rotation of a seesaw, there's no movement. There's no rotational movement. Okay, so same case here. The reaction force, it can exist here, but there's no rotation because it is at the axis of rotation. Apply lah banyak mana pun, tak gerak sebab dekat axis of rotation. So here, torque number 1 is just 0. You can write it nicely. If you want to put in the equation, boleh. So this is going to be R sine theta F. This is going to be 0 sine unknown because we don't know the reaction force angle yet. The force is R. Boleh, but it's just going to be 0. Okay. So the next one. Sibuknya orang tu. Okay, next one. Tension. Can you guys hear that? T is for tension. My God. So tau number 2. Torque number 2. Jangan copy mami. Okay, next one is RF. Okay, so what is our R over here for torque number 2? So everyone's like asleep. Do we need a break? Sekejap, kita habiskan ni, kita take a break after this. I know it's heavy stuff. So what is our R? Come on guys, you need a break, right? So cepat habiskan yang ni.
L.
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 Okay. What is my F? What is my F for this
T.
guy? Tension, right? Tension. What is the angle? It's just theta, right? We don't know.
Theta.
Sine theta. So L, T as in tension, sine theta. So this is torque number 2. Torque number 3. Does the weight of this beam contribute to rotational motion or not? So if I sit over here, will I contribute to the rotational motion? Yes, the answer is yes. So since we are defining the weight of the beam over here, therefore the weight of the beam also contributes to the rotational motion. Benda yang berat akan menghasilkan rotational motion because dia ada gravity, right? So the gravity can actually tarik and make that rotational motion. You guys can imagine it like that. So for torque number 3, we do have rotational motion and the length or the radius between the axis of rotation to the weight of the beam is L over 2. How do I know it's L over 2? Because it is at the center of the object. So this becomes RF. It is equal to L over 2 times with weight, mg of beam, and the angle between the radius and also the weight is 90 degrees. Okay, so now I add all this together. So this guy is 0. This guy is L tension sine theta. We don't know yet. This torque number 3 is L over 2 mg sine 90. So this is exactly what we have over here. Tapi direction kita tak define lagi. So now we have to define the direction. So imagine all these forces tak ada. We're just talking about tension. So if I resolve tension into its perpendicular component, which direction would it go? Is it clockwise or anti-clockwise? Anti-clockwise?
Anti-clockwise.
Okay, anti-clockwise. So it's going to rotate this way. So we know that tension is going to be, torque number 3 is going to be positive. Tak kat sini jap. Tak nampak lah. Will blue nampak? Tak nampak juga. Hitam lah. So this is going to be positive torque. What about torque number 2? So this is already perpendicular. So which direction would it rotate? Clockwise or anti-clockwise? Rotating the beam. This way or this way? Clockwise, right? Clockwise. So it's going to be negative. And for the reaction force, it's 0, so we don't really care. So this one becomes, kenapa dia cakap positive, negative kat sini? Sekejap. Anti-clockwise is positive. Saya silap tulis. Anti-clockwise is positive. Kat sini. This is anti-clockwise, right? Anti-clockwise. Okay, betul. So this is negative. Okay. So my net in the T ataupun net in the torque is equal to T sin theta L. Sama tak? T sin theta L sama minus, this is minus L mg sin theta L over 2 ataupun W sin 90 L over 2. This is mg sin 90 L over 2. Okay. So let's take a break and then kita akan cuba like organize our thoughts balik. Let's take a 6-minute break. So 3:18, please come back. If you have any questions, you can ask me. If not, please take your break and come back refreshed. Gosh, this yellow is not nice. Okay. And this one contributes to this way, clockwise, anti-clockwise. This is going to be negative. This is going to be positive. Oops. Saya tu silap. Negatif. What if T3 is clockwise? T3, torque number 3. Torque number 3 was this guy, okay. So net torque tu tambah instead of minus, right? Yes, Rachel, betul. Kalau clockwise, dia tambah je lah. Net torque tu tambah instead of minus. No, clockwise will become negative. Okay, so if this thing is moving downwards, clockwise, so semua jadi negatif lah. So it will have a negative torque. A negative torque just simply means it's rotating in clockwise direction. It's not exactly a bad thing. It just tells us the direction. Let me write this way. AC. Nak doktor lain SpongeBob ke? SpongeBob ke? Taklah, dia tengah main game apa entah, game budak-budak. Macam mana tahu dia lain SpongeBob? Tapi adalah dia tengok SpongeBob sikit-sikit. Is it time yet? Belum. Sorry, terlebih masa pula. Okay, so I hope everyone is back and ready to learn. Okay, so we talked about this cable that was connecting a beam to a wall, and the beam has a hinge over here, and I told you when we have a hinge or an axis of rotation, we put in our reaction force. However, we don't know the direction of our reaction force, so we just label it as Rx and Ry. So if you want to not label it like this, you can also write it like this, R. So this becomes your unknown. So your R can be resolved into its X and Y by an angle, right? Macam biasalah. Tapi kalau kita nak terus resolve, kita terus tulis Rx and Ry. I prefer it this way. It's easier because we will have to solve it in X and Y anyways. So better to use Rx and Ry immediately rather than defining it as R. So let's stick with Rx and Ry. So we found out that the tension over here has a radius to the axis of rotation as L. So from the axis of rotation to the point of this force is L. That is the radius and this is the force. However, the force is not perpendicular, so we have to resolve. So this becomes T sine theta. Ataupun if you don't want to do it that way, we can just use the R cross F method, which was R sine theta F, which is sine theta, or theta is the angle between R and F. Or you can just simply resolve it, find out what is the perpendicular component to the R, and it is just simply T sine theta, which is exactly the same thing. So you can choose to resolve it, or you can choose to use this equation. Okay, dua-dua boleh. Whichever works for you. Okay, so we are, oops, why did I do that? So T is, when we resolve it, the perpendicular component of tension is going upwards. And if we have a beam and I push this beam this way, I'm applying this much force, right? So the rotation is going to be going upwards, and upwards means anti-clockwise. So anti-clockwise torque, a torque that is anti-clockwise will give me positive, a rotational motion that is anti-clockwise will give me positive torque. And then for the beam has a radius of L over 2. How did I define that? Because the weight of the beam is at the center of the mass. So this is L over 2. And the direction, if I have a beam, I'm pushing the beam. So the rotation will be clockwise. So clockwise gives us negative torque. And then our reaction force that we already resolved terus kat sini, Rx and Ry, it is at the axis of rotation. R is equal to 0. Therefore, torque is also equal to 0. So kita tambah apa yang ada dekat sini. So this is going to be positive. T sine angle, don't know what the angle is. T sine theta times with L is going to give me positive. This is the positive component over here. And this guy, W times with L over 2, and the angle is sine 90, is going to give me a clockwise rotational motion. So it's going to give me negative. Okay, so this is what we have. We're not trying to solve it. We're just talking about the free body diagram and the equations. So how do we solve it for force? So now we combine all these forces at one center of mass, just like we did in chapter 3. So Ry becomes over here, Rx is this way, and then the torque is this way, it has the same angle, and then our weight of the beam. So net in the Fx is going to be minus T cosine. Macam mana kita resolve ni? Minus T cosine theta. Kenapa saya pakai crayon? This is a bad pen. Okay, so this is going to be T cosine theta, and it is negative because it's going to the left, sama. And this is going to give me T sine theta, positive. So this is the Y component. For Ry and Rx, you just put it like this. Kita tak tahu apa lagi. And for the weight, it has a negative W direction, and it's X component is non-existent, so it's just 0. So typically we write this as net in the fx is equal to minus t cosine theta plus rx plus 0. You can ignore the 0 if you want. Net in the fy is equal to t sine theta plus ry minus w. So if you have the other values, you can solve for r depending on the question. So it's not really about the question, it's about understanding the free body diagram and knowing what is your x and what is your y. That's the most important part. Okay, any questions about this one? Is everyone okay with this? So anti-clockwise is positive, clockwise is negative. Just now, Rachel asked me, what if the tension is going clockwise? What will happen to the equation? The equation will be minus t sine theta L minus w sine theta L over 2. It doesn't really matter whether it's positive or negative. The positive and negative just tells me the rotation is either positive, either clockwise or anti-clockwise. So if this magnitude gives me positive, oh, I know that the rotation is going to be anti-clockwise. If this whole magnitude gives me a negative, oh, I know that the rotational motion is clockwise. It doesn't mean, if a negative torque doesn't mean a bad thing. It just tells us it's clockwise. Itu sahaja. Okay? So no questions? Alright, so I'm going to move on. If you have any questions, please interrupt. Okay, so this is a man holding a ball. So imagine tangan sendiri. Tak imagine lah, pakai je tangan sendiri. So this is our arm. We have the axis of rotation over here dekat siku. Our siku, our elbow is actually our axis of rotation. So if I'm holding something heavy, this is going to be my force. Lemak tak nampak pula. Oh my god, my hand disappeared. Need to make this bigger. Okay, so how do I make this? I'm going to try again. Hopefully my hand doesn't disappear. Okay, so I'm holding something. This object has some weight, right? So this is already mg down here. Kenapa dia hilang? I don't understand. It's so hard. Okay, so this is mg. This vitamin bottle is our mg, is an object. And if I apply, macam nak cakap? Susah pula. Oh, what is an example? Let's just use this same example lah. So this is our siku. This is our axis of rotation. This bottle has mg. So if this is like super heavy, like it's a dumbbell instead of like a vitamin bottle, my hand would go like downwards, right? So it will contribute to a clockwise rotation. So if this guy is like super heavy, kan, kita akan macam tangan kita terjatuh kan. So it's like a clockwise rotational motion. Walaupun siku kita tak adalah fleksibel nak rotate habis kan. But we know that it has that tendency to rotate clockwise direction. Walaupun dia tak berlaku macam tu sebab kita punya tangan tak berapa fleksibel. So if it is not that heavy, then sikit je lah rotational motion dia. Tapi kalau super heavy, like a dumbbell, so it's like going all the way. It's going to like super flex, right? So the force applied by the object that we're holding has the radius from the axis of rotation, which is our elbow, and this is our radius. So sama juga kat sini, this is the force, this is the R, axis of rotation. You have your torque. Your hand, your arm has torque. So back to this equation. Penatlah demo-demo pakai badan ni. Sebab macam tak nampak lah apalah. Okay, so we have talked about the force of this object. And then this is the weight of our arm. Sama juga, all objects will have weight. The seesaw, the beam, our arm, it will have its own weight apart from the weight of the object that is holding ke apa ke. So it will have its own weight. So this is weight number 1. Weight number 2 is the weight of the ball, and it is contributing to a clockwise rotational motion. What about the weight of our own arm? what direction will that contribute to? Is it clockwise or anti-clockwise? In this position
Clockwise.
specifically, clockwise, right? So it's going this way as well. So clockwise and clockwise. And then we have, at the axis of rotation, we have our reaction force. How do I explain the reaction force here? But in axis of rotation, memang kita letak R. I don't know how to explain siku punya situasi. I don't exactly know biology. So, but we know that axis of rotation is R. So kita letak je lah Rx over here and also Ry. Wow, ada tension pula. I don't know how that works. Kenapa ada tension Sebab ada muscle kot. Okay, let's just go with this example. So we are going to assume that our muscle has some tension if we are holding an object. Oh, betul juga. When we're holding an object, we have to like use this part, right? We have to use our, what do you call this? I don't have any muscle. We have to use this part and it has some tension. Biceps, yes. Thank you, Taiba and Daniel. So we use our biceps to, this guy applies some tension lah to really hold a heavy object, right? So this is why like dorang macam tu kan, when they're holding a heavy object. Don't know why they do that word, the sound. It's not necessary, but they do it. Okay, so we have our tension over here is acting upwards. And again, I don't understand how it works because it's biology. Tapi kita akan go with it. Let's just talk about it in terms of torque. So in terms of torque, will the tension contribute to rotational motion or not? In terms of torque.
Yes.
Yes, because.
Perpendicular.
90 degrees.
Okay, that's one thing. What is the other condition to have rotational motion? So guys, kenapa kita tak ada kenapa torque tak ada kat reaction force? Why was it 0 in the first place? Okay, let's go back.
R.
Sebab R kosong, betul tak? R kosong.
Yes.
Okay. Does tension have R? Yes, it's not at the axis of rotation. Dia specifically labeled kat tepi sikit. So yeah, tension has R walaupun kecil. Okay, so this is the small r over here. So but they label it as L1. So the weight of your arm has L3 as its radius. What is the radius? It is the point of the force applied to the axis of rotation. Tension of your muscles to the axis of rotation is L1. And then for this guy, this is the heavy object that we're holding. In this case, it is a bowling ball. So weight 3, this is the force. And the radius of the force to the axis of rotation is L2. Kat sini label. Okay. So kita now the next step is to identify whether it's going to contribute to a positive or negative. So tension, if we apply tension over here, will it contribute to a clockwise rotation or anti-clockwise? Clockwise or anti-clockwise?
Anti-clockwise.
Anti-clockwise, right? Because kita bayangkan macam ruler lah. We push it upwards, it's going to go anti-clockwise. So it's not really obvious when you're looking at your own body. Tapi kita imagine like a ruler. And if they show us that the force is going upwards, we push our ruler. And if it goes anti-clockwise, then that is your answer lah. If it goes down, push it, it goes clockwise. So that is your answer. So this one clockwise, this guy anti-clockwise. So this guy gives us positive torque. The weight of our own arm gives us negative torque. The weight of this object gives us negative torque. So here we have positive, negative, negative. T L1, the small l, T L1 is the first torque. The second torque is W1 with L3 down here. Salah, dia macam rata-rata. Okay, kat sini. And this one over here. L2 with L3. So they are all perpendicular, so we are just ignoring the angle. So Rachel said here that when you are holding a heavy object, you tense up your muscle. Therefore, it creates tension. I don't know. I really don't know these things. I'm so sorry. Tapi betul lah kot. I would imagine it to be like that. Okay. So this is our torque. What did we do here? We defined our axis of rotation. We identified the forces. We identified the radius, and then we decided whether it is going to contribute to clockwise or anti-clockwise. So let me write down the steps here. So first, define axis of rotation. Whoops, of rotation. Second step is to define the forces and the radius. Third step, identify direction. Identify anti-clockwise or clockwise. So anti-clockwise will become positive, clockwise will become negative, and then you put into your equation. Okay, so if we're talking about the forces, remember when we are talking about equilibrium, we have to know the translational forces and also the rotational forces. So for the translational force, we combine all of them at the center of the mass. So just letak je lah. So tension macam ni. Then we have Ry, we have T, we have our Rx over here, we have our W1, and then we have our W3. Am I missing anything? Okay, sama. So it's just like combining everything into one single point. So then you know that your net in the Fy will be T plus Ry minus W1 minus W2, and your Rx is just Rx. Like this one. Okay. So for the first part, I think it's straightforward. You just have to remember how to do the free body diagram and the equations for torque. This is new to us. So do I have any more questions about this? Sorry, Dr. W2 with L2, right? Sorry, W2 with L2. W2 with L2. Where's W2? W2 with L2. Oh, dia silap tulis ni. W1 is here. This is L3. And then this is W2. This is L2. Where's the L2 here? Clockwise. So just dia tersilap kot. W2, L2. W1, L3. This one. Okay. Let me try this. Betul lah kan? W1, L3. W2, L2. Tension with L1. Okay, betul dah. Okay, so silap kat sini sikit. Sorry. Good eye. Let me write this. This is W1, L3, W2, L2. Okay. Okay, next one. So kalau soalan, please interrupt me. How much time do we have left? Okay, we have time. So the next one is this one. It is a beam again and a string. But this time the beam is like slanted. It's not straight, right? But again, our axis of rotation will have the reaction force. Kat sini dia define Ry ke bawah, Rx ke kanan. Tak kisah sebenarnya. You can actually define your Ry to be this way and Rx to be this way. So if you get a negative Ry, you know that is going down. If your if your arrow that is already going downward and you get a positive value, you know that it is actually going down. So I prefer you guys to go with the conventional sign, which is Ry, Rx. Let's just go for the positive ones. Sebab kalau defined as negative, you have to remember that if you get a positive, it is correct assumption. If it is a negative, it is wrong assumption. So that's like extra work. So just define it as positive Ry and positive Rx. So kalau dapat negative Ry, you know that it is supposed to go down. If you get a negative Rx, you know that it is supposed to go left. Macam tu je lah, lagi senang. So let's define it like this. What else? We have tension here because we have a string. It has some angle. Kenapa dia define kat sini? Tak apalah. And then we have weight. Our weight is always going downwards, but it is not perpendicular to the R. Just now, our beam was straight, so anything that was going down or going upwards will give us 90 degrees angle. But since our beam is now slanted, this guy is no longer 90 degrees. The angle between R and the weight of the beam is no longer 90 degrees. So dia jadi slightly harder. Okay. And then the tension is also dah jadi susah sikit lah. Tapi as long as we know what is the angle, we can solve for the torque. Okay. So here, they calculated 180 minus 180 minus 20. Kenapa dia cakap ini 180 minus 20? Sekejap. Oh, okay. Dia nak tahu yang ni. Let me erase this. Okay, so this is like a straight line, right? This is like a straight line, and you know that a straight line macam ni akan ada 180 degrees. So if one part is 20, we want to know what is the other part. So we have to do 180 tolak 20. So this is what they're trying to do here. So this is 20 degrees. Therefore, this part over here is 180 minus 20. And this is a triangle. And a triangle has, the total angle in a triangle is 180. Therefore, if this triangle has 180 and you know that this one is minus 180 minus 20, you would know that these two angles are going to be, it will be equal to 2 theta. Okay, let me repeat myself here. So we know that this angle is 180 minus 20. How do we know that? Because kita dah cakap kat sini, if a straight line, when we have a straight line, and we know that this part is 20 degrees, therefore we know that this other part is going to be 180 minus 20. So this is 180 minus 20. Now, the total angle in a triangle must be equal to 180. This is like modern maths back in high school. So the total angle in a triangle must be 180. So kalau kita tambah semua angle dalam ni, theta plus 180 minus 20, we will get 180. So I'm just rearranging this equation. So 180 minus this guy will be equal to 2 theta. So this is how I got this equation. So now 180 minus 180 is 0. Minus with a minus 20 is a positive 20. So 2 theta, 20 is equal to 2 theta. Therefore, theta is equal to 10 degrees. Betul ke? Betul lah tu. Okay, so we solved that angle. So now we know that the angle between the tension and also the R over here. So we can try to solve it now. So here we have T tension, sine theta, the length is L. They define it as L. Sorry, we have a better diagram over here. The length to the axis of rotation is L. So this is L. Okay, so T sine theta, L. What is theta? Theta is theta. Theta is 10 degrees. And then this guy, if we resolve it, kita ada pembaris, kita tolak dia ke arah yang sama dengan tension yang perpendicular. We know that it will go anti-clockwise, so it will get a positive sign. Next one, weight. So here we defined it as 20. Oh, this is 2 theta ke 20? I think it's 2 theta. Why is it 2 theta? Oh yeah, it is 2 theta. Okay, tak apalah, it's just angle. Nanti kita solve kemudian. I want to talk to you guys about the free body diagram. That's the most important part. The angle is just modern maths. It's just geometry. Okay, so this is, if we resolve the T, okay, this is going to be our T perpendicular to the R. We know that it is going to go anti-clockwise. So it will get a positive torque. And then for the weight, I push it down. I know it's going to give me clockwise. So it's going to be minus W. The length is going to be half of the beam. So this is L over 2. The angle will be whatever angle between the R and also the W. Kenapa dia pakai 2 theta? Sekejap Because this guy is here. This is the perpendicular component. Okay, betul. So dia pakai 2 theta kat sini sebab if we resolve weight to become the perpendicular component to R, this is our R, right? This is going to be W sine 2 theta, which is what is over here lah. Okay, so always try to resolve your forces into its perpendicular component and then define your angle that way pun is much better. So this was a quite tricky example. So this is our torque that we have. We only have 2 forces that is not acting on the axis of rotation. The reaction force we ignore because it is on the axis of rotation, therefore R is 0. For the forces, we combine everything at the center. So we have the x component as Rx. This guy becomes T sine theta. Wait. Aduh, malas nak buat. Oh, this is like chapter 3 all over again. Okay, I shouldn't be lazy. I should be a good example to you guys. Okay, so Rx is this way. They define Rx macam ni. So this is this way and this way. Okay. Focus. So W is this way. Okay, Ry is this way. Okay, betul. Tension is this way. I want to resolve it to become this way and oh, okay. This is important actually. So this way. So here for your torque, your axis was actually R. Kenapa saya tak perasan benda ni? Sorry. Okay, so let me recap here. So what happened here when we have a beam that is not straight? When we have a beam that is not straight, we define our R to be slanted as well, right? And we try to find the perpendicular force with respect to the beam, which means that the T that I resolve would be this way, the T perpendicular that I resolve will be this way, and the W that I resolve would be this way. However, when we're talking about forces, we want to use the actual x-axis and the actual y-axis. So in this case, the actual one is not following the beam, but it follows the actual y and x-axis. So W goes down, Rx to the right, Ry down, and T, we have to know the T is this way, right? We have to know what is the component of T. It's not the same as we're solving for torque. The torque that was perpendicular to the R was different than the tension that we used to find torque was different compared to the tension that we use in the free body diagram for translational force. Does everyone get me on that one? Faham tak apa yang saya cakap ni? Should I repeat myself?
Yes.
This is important. Okay, so everyone please focus. I'm going to repeat myself here. This is very important. If your beam is not straight, which is what we have here, our beam is not straight. So when we are talking about net torque, right? When we're talking about net torque, I need to know what is the perpendicular force acting on the beam. So what we did was we resolved with respect to the beam. We resolve, this is our axis, and we resolved our W perpendicular with respect to the beam. We resolved our T perpendicular with respect to the beam. And this was T sine theta times with L, which is the radius. And this becomes W sine 2 theta L over 2. This is T sine theta. Okay, so everyone following me on the torque part? Fahamkan part torque dulu. Everyone okay with torque for this point?
Okay.
Okay, eh?
Okay.
Any questions about torque before I move on to the force? No questions. Okay, so now that we define the tension perpendicular to the beam this way, right? And our weight of the beam that is perpendicular to the beam, this is not the same as the force for translational forces. Okay, so for this guy over here, we defined the X and Y not this way, but we defined it this way, X and Y, like that. So now, if I define it this way, instead of the direction of the beam, the Rx is this way, the Ry is going down, the weight is going down. The only thing that is not on the axis is just T. Okay, so the only thing that is not on the axis is T. So T is over here. The angle is theta over here. Kenapa letak kat sini Kejap. Kenapa letak kat situ Kejap. This is the angle over here with respect to the x-axis. What is the angle here? Theta. Is this an unknown theta? I think they defined a new theta here. Okay, so my point is that the T that we resolve perpendicularly for the torque and the weight that we resolve to be perpendicular for the torque is not the same as the forces for this guy over here. Untuk table ni, semua tak ada resolve. Weight kita pakai as it is. We didn't resolve it to be perpendicular to the beam. Our tension kena resolve. So the weight, we just use it as it is. The R, we just use it as it is. Rx, we just use it as it is. For torque, we did not use it as it is. We had to define the weight that is perpendicular to the beam. So tu perbezaan antara torque dengan force biasa. Torque follows the direction of the beam. Force biasa, we use the axis that we define. With that being said, can I change my axis to become the same axis as the beam? Can I do that or not? Boleh actually. You can. So, kalau kita define our axis for the force, this is our X and this is our Y, my free body diagram would look different than this one. So, let's draw it. Kalau saya define my X and Y like this, so what is in my X? I have my R. So this becomes over here, Rx. This becomes over here, Ry. And then we have our tension over here. So it becomes, this is the theta over here. This is the angle between here and the tension. Sebenarnya boleh. Because the axis for forces is what we define. Remember we had like incline versus level ground. We defined the axis ourselves, right? We had like a slanted axis versus a normal regular axis. Sama juga kat sini. We can assume this is like an incline. But this makes our life hard. We don't want that. So let's just use this regular axis because a lot of our forces are in the regular axis and only the T is not. So better use that approach. So my point here is that for the torque, it is always about the force that is perpendicular with the beam or the radius. For force, we don't really care about that. We only want everything in the same axis. So kalau semua ramai-ramai dalam x-axis ada dalam axis yang sama, contohnya kat sini ramai force ramai. Banyak force dalam y-axis, dalam axis yang sama, so kita pakai this axis. This is how we chose this axis. Sebab ada banyak force in this axis. Does that make sense? It's a little bit complicated. Okay tak? Everyone okay? I know it's like petang and tak sabar nak habis kelas. I get it. Any questions? So everyone's okay? Okay?
Betul.
Yes.
Yang tadi doktor kata yang RY tu ke atas tapi yang dalam kotak
Oh, okay. Boleh.
Force ni
Kita
ke bawah.
adjust. We can adjust it. So, oops, sorry. Singat pula. So this is RY. Let's get rid of this. So this is our RY. So therefore, we have our RY over here. Kenapa saya punya line tak boleh nak straight. This is our RY. Ni tak ada. So it becomes like that. So dalam equation, dia akan jadi positif. Apa lagi yang saya tak ada lagi kat sini. So torque is not affected by that because RY and RX is at the axis of rotation. So this is remain correct. But for the forces, our Rx is positive and for our Ry, it is positive. So the equation will be net in the Fy, Ry positive minus weight. And then for the x-axis, net in the Fx, we have minus t sine theta plus Rx. So if they tell me this guy is not moving, the system is in equilibrium. So I can say, oh, net in the Fy is equal to 0, net in the Fx is equal to 0. Therefore, I know that the Ry, reaction force, is equal to weight. And Rx is equal to tension sine theta. If they tell me that, but they didn't. So we are left hanging. Don't do that to people. Okay, so that's it for class today. We will continue next class. For next class, I need to confirm with you guys on the chapters for quiz and also final exam. For your penilaian 2, I hope everyone is aware because I already told this one. 3, 4, 5. Penilaian 2. 3, 4, 5. Okay. The next class, I will confirm on final exam and quiz punya chapters. And also continue on this chapter. Habis. Oh, we have another example, but never mind. Kita akan buat kemudian. Okay, that's it guys. Have a great rest of the day. Take care. If you have anything to ask, you can ask me. If not, you're free to go. Bye.
Thank you, Doktor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Doctor.
Thank you, Doctor.
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 Bye.
Bye.